Hello everyone. We are starting with the other aspects of the scalar and vector field. In our last lecture, we have discussed about the gradient, divergence and curl of these fields. In this lecture, we'll try to integrate these fields with respect to different regions. So in this talk, we are going to discuss about the vector integration, line integration, surface integration, volume integrations. So starting with the vector integration, so here we are considering if any vector v who is a function of t where t is a scalar variable, then the integration can be written as integration of v dt is equal to integration I v x t plus j vy t plus k cap v z t dt, where v vector can be written like this. So we can solve and we can the integration can be separated out for all the three axes, like I cap integration vx dt plus j cap integration vy dt plus k cap integration vz dt is like that. So we are going to line integration. If we are integrating along a line, then it is called a line integration. Or if we are integrating along a curve, it may or may not be a straight line, then we can term it as a line integration. Here we are considering a vector v who is a function of x, y and z. If we are integrating from point P1 to point P2 over the curve C, then the integration can be written as integration I is equal to integrating v dot dl along the curve C, or it can be written as integration from point P1 to P2 v dot dl. So in physics we usually encounter some similar examples for a line integration. Suppose we have to find out the total work done by any force F along the curve C from point x1 to x2 along the curve C. So we have to find the work done dw. So it can be expressed as integration x from x1 to x2 f dot dx. If this integration is path independent, then the force is said to be conservative force. For example, electrostatic force, gravitational force are path independent. That is, the work done doesn't depend on its path. It can take any path, but with under the condition that in the starting and the final point remains same. Some other kind of forces are there where the path does matter. If the starting point, if we start from some point x1 to x2 through different paths, then total work done may depend on the path itself. So we may cite frictional force in this regard. So these forces are non-conservative in natures. Now we are going to the closeness. If we consider the line integration over a closed curve where the beginning and ending point are same, then the line integration is called a close, and it can be written as I equal to close integration v dot dl. Now coming to surface integration, this is the integration of a vector along any arbitrary surface or plane is called a surface integration. We consider any vector v over the space xyz. Then if we integrate along the surface S, then we can return like this is integration is I equal to integration v dot ds, where S is the surface. For closed surface, we can write this a closed symbol for integration, closed integration v dot ds. For example, we can calculate total current flow from the current density over the area dA. We can represent like this. Now coming to volume integration, the integration of any scalar field over an arbitrary volume is called the volume integration. We are considering a scalar phi which is a function of x, y and z. If we integrate over the volume tau, then the volume integration can be written as I equal to integration over integration of phi with respect to the volume d tau. So if we are allowed to find the total mass of a system for given volume tau, if rho beta density, there is mass density of the system, then the total mass of the system can be written as integration rho d tau, is like that. So in today's talk we have learned what is line integration, what is surface integration, and what is volume integration. So in our next class we will continue with two different theorems where we can convert from volume integration to surface integration, and from surface integration to line integration. Thank you for listening.